Okay. So, oh, sorry, we're up to doing some matrices ones now. So with this one, it said the matrix V is an n by n. So write these things in. So n by n means it must be square. Okay, so then that helps you know. So and a square, and then it says with a determinant equal to 0. To equal to 1. So if that means if it's the determinant is not 0, that means anything but 0. So an inverse can be found. So that means like you can. Okay, so that can help us with things. So it said the product of V by VI will result in. So so that's pretty much the inverse there. And because you can find the inverse, if you divide a matrix by its inverse, it will always produce the identity matrix. So it will result in that. So that is the best answer. So you knew that it's a square, and because that determinant equals 1, you can find an inverse. So that's what you're relying on. With this next one, it said matrix J is a row matrix with an order of 1n, and then it says K is a column matrix. Now it's saying J transposed, JT is that. So that means the rows and columns are swapped around. So you may as well just write the order there. So that would become an n by 1 the other way round, and K would become a 1 by n if that was transposed. So then off you go and you answer which ones are defined, or consider the following matrix. Which ones are defined? Defined means you can actually do it. Now, if you look at J squared, if you look at J is not a square matrix. So you can only, so this is definitely not defined, because you can only raise square matrices to a power. So we definitely can't do that one. So that one's out. Now, that one. If you are going to check, you should go check the other ones. Just going to change. Like you can just put the orders. So J's first, so it's a 1 by n, and then K, which is an n by 1. If you do that, that one's defined. And you just keep going through them all, and you'll notice that all these ones can be defined. So say if I do K transpose was a 1 by n, and J transpose was an n by 1. Yep, they're the same, so it's okay. So it ends up being the 4 there. Okay, let's just remember that square matrices are the only ones that can have a power. All right, this one I just want to bring. They've brought this up before in other exams, so we need to make sure of this. A group of meerkats live in an enclosure at a zoo, and we can see they either in chamber A or chamber B, and they transition from location to location at night. But the important fact is right here. It says that every night there are A meerkats at chamber A. So that means there's a set number and it never changes. So the numbers at A stays the same, because they said it was, stays the same. So when we say if it stays the same, therefore it goes, what goes out? So if a meerkat goes out, must come in. The same amount goes. So what goes out must come in. That's what it's saying. So we had one similar about an airport parking. I think cars came out. So, and then it says, so then we know that. And it's the same situation for B. What goes out must come in. All right. So of the meerkats sleeping in chamber A on Friday night, 8 had slept in chamber B. So what we've seen there is they've just told me if I was at B and I went to A, 8, so it said 8. So then what you can see, so this is the B amount and this is the A amount. So really what we can say is 0.2 of the B amount equaled 8. And remember, if 8 went out, then 8 went in. So then you can also say then 0.4 of A equals 8. Okay, so and then there, so then all you have to do is you change them to a fraction, decimals or whatever. So 0.2 times B equals 8. Well, if you can either solve or rearrange, so B equals 8 divided by 0.2, so which equals 40, and then A would have equaled 8 divided by 0.4, so which equals 20. Now it said how many meerkats live in the enclosure, so that's total. So you need 40 and 20, so it ends up being 60. Oh, I didn't press record, you dog. Did I? No. Why is it if 8 goes out, 8 has to come in? Because they said there's at night there's a amount, so that's a number, and it means it doesn't change. It's a constant. So if I move 8 out, if eight of them decide to go, it means 8 come from the other guy. So it has to. Yeah, it's just because they said that every night. Otherwise, you can't work it out. And there was one in our notes. You'll see it in the notes. It's under the plane thing. Oh, it is recording. Okay, online shop offers monthly subscriptions for protein powders. There's 3 powders: chocolate, vanilla, and malt. And let PN be the state matrix that shows the expected number of subscribers for each flavor after N months, and blah, blah, blah. So you can see we've got a transition, but we've actually got a recurrence relation. So when we see these recurrence relation, that's a recurrence formula, you can do none of the power tricks can happen with this. You always have to go step by step. So here's a thing, and so this is the rule of how to get the next month of prescribers, and you can see you've got to add K, and they've given you that there. All right, and they've given you P2, okay? So the increase in the expected number of subscribers for vanilla between the initial sales PO and the first month P1 is equal to. So pretty much we need to know what PO and we need to know what P1 is. So we don't have them, but we have one. So if you think about it, we've got P2. So if I wrote P2 here and I write down how we found P2, we would have gone the transition times the one before, which would have been P1, and the formula also says to plus K. So that's what we would have had. So we've done that. So if you look at what we have P2, we have the transition, and we have K. Okay, so I could rearrange this so that we can find P1. So what would move over first would be the K. So because it's adding here, it'd subtract. So you'd have P2 minus the K. That would be the first thing you move. And then once you've done, and that would equal what's left here, the transition times P1. Now, because you want to get the P1 by itself, we would move this. Now, that's timesing, which means we want to divide. We don't divide in matrices. We use the inverse. So I'm going to use the inverse, which is the -1. And I would have done this. So what we're doing, and that will give me P1. And then once you've got P1, you will go off and you do the same thing to find P0, because what P0 would equal, it will be the same formula there. You'd do the you'd have -1, and what you would have had is you would have had P1 minus the K. So we need to first do this one, get the answer and pop it in, and then do that one. Then we'll have P1 and PO. So I'm going to do it here on our calc. So just on a normal page. All right, I'm going to pop in our transition, which is a 3x3. So that's handy. 0.2. I'll pause it while I type it all up. All right, so what we want to do is we essentially want to do the transition to the negative power. So I've typed them all in here just to get us going. So here's the transition to raise to a negative power, and we would times that. And what we did, we moved this P2 and K over first. So you need to have that in brackets. So the brackets are important. So I've opened the bracket and I had P2, which is this matrix, minus K, which was that one. And then closed the bracket, and then we times it. So in the end, we end up with if I get P1, I'm just going to put that there, is 120, 98, and 104. Now, then we pretty much did the same thing, except we don't want P2 in there. We want P1 in it. So I'm just going to go back to my calculator, and I'm just going to highlight that. And I'm obviously changing this one to P1, which was 120, 98, and 104. So you do it again, and here you get P. So PO would have equaled 60, 49, and 52. Now, the thing they actually asked, there was an increase in vanilla. So vanilla was so the increase expected is subscribers vanilla between the initial sales of PO. So here's PO, so vanilla to here. So you went from 60 to 60. And it said the increase in numbers is equal to what? So if you went from 60 to 120, it's 60. Yeah? So that C is the answer.